So this was a study made in collaboration between the Università degli Studi di Parma, the University of Parma, and Asphalt Rubber Italia. And my co-author is the professor Felice Giuliani. So, what we considered, now in Italy there's a lot of confusion because we are starting using asphalt rubber, and there's some confusion between the dry method, the wet method. Many people point many difficulties of producing asphalt rubber, and we also have access to few information of terminal blend. And people start asking, what's the difference between asphalt rubber and terminal blend? And we consider that asphalt rubber is a modified binder with at least 15% of crumb rubber, while a terminal blend is a crumb rubber modified binder, but with 10 or less %. Usually, this kind of formulation has some additives or some extensive oils. And the question was, but is it possible to pass from a formulation of asphalt rubber to a formulation of terminal blend with the same performance, with the performance that we know that asphalt rubber has on the field? So we decided to make some conventional tests, easy to explain to people, and to see what happened. We started to see the influence of increasing, considering asphalt rubber formulations, increasing the percentage of crumb rubber in the main properties of the material. So here we can see the relationship, and it's very intuitive, of the softening temperature point and the viscosity. Of course, increasing the percentage of crumb rubber, we increase viscosity and we increase the ring and ball temperature. Considering the same rubber, here we are speaking same rubber, changing the base material, so considering a 70-100, a 50-70, and a 40-50 binder, we can see that we have different results. So if we have a softer base, we have a better interaction to what concerns to increasing the softening temperature, and viscosity, of course, is greater for 50 and 70 and for 40 and 50. This was just to be sure that what we felt from the beginning was right. Considering now resilience, the results show a different thing, that there was a better interaction between the 70-100 than with the 50-70. So for the 20%, we can see that this one has better performance. And then we went to see what happened considering the terminal blend formulation. In the market, in Italy, we have also in the market additives that are based on polyphosphoric acid. This is the formulation, some characteristics, and we know that this kind of additive is used since the 1997 in the North America as a chemical modifier agent for bitumen, and since 2004 in Europe in both wet and dry process. To what? To low viscosity in order to increase workability, to solve some storage problems, and also to substitute extender oils in the formulations. So what we did is considered for the same percentage of crumb rubber, which is 8%, increase the percentage of polyphosphoric to see what happened. And we have viscosity at 160, which is the Italian normative, at 175, which is for the asphalt rubber normative. And we can see that increasing the percentage of polyphosphoric acid, we increase the viscosity. And that was something that we didn't expect. To what concerns the influence of the percentage of polyphosphoric acid in softening temperature, we had the same result, so increasing the percentage of polyphosphoric acid, we can see that we have a higher softening temperature. But we can take the same conclusion by keeping constant the percentage of polyphosphoric acid and increasing the percentage of crumb rubber. Same conclusion for resilience. Increasing the percentage of polyphosphoric acid, we can increase significantly resilience, but increasing the crumb rubber, we can also increase resilience. So the conclusions we could make after testing several binders is that 0.5% of polyphosphoric acid corresponds to an increasement in terms of resilience and ring and ball of 2% of CRM. Then we said, okay, so let's see if this is happening because we are working with small amounts of crumb rubber, and what would happen if we add this same polyphosphoric additive to asphalt rubber. And here we can see that this is a conventional asphalt rubber, 20% of asphalt rubber, and we can see that increasing that adding the polyphosphoric additive, we have an increasement of viscosity. And here we can see that viscosity actually gets higher with the percentage of crumb rubber. And the same conclusions for resilience, but one important aspect of the research was to see that there was no quantity of polyphosphoric acid that could increase resilience as we reach to a regular asphalt rubber. But adding 1% of polyphosphoric acid increases significantly resilience. The only thing is that here we are very close to what's the limit of asphalt rubber, and we didn't solve our problem of workability. Another thing that was important was to study the storage stability. We decided to consider two methods, static and under agitation. And this was a very good result because one of the aspects that we know that perhaps it's the lack of asphalt rubber is that it has a very low storage stability. But with the addition of 1% of polyphosphoric acid, we managed to have better storage stability. Then we decided to see, okay, this is what happened with rubber, and what if I added this kind of additive to SPS? And we had pretty much the same results. So we have an increasement of viscosity with the addition of polyphosphoric acid, increasing the percentage of SPS. But the same results were achieved adding 1% of EVA. So what we can say is that in terms of increasement of ring and ball temperature and viscosity, the addition of 0.5% of polyphosphoric acids corresponds at the same addition of making mixes containing low percentage of SPS plus 1% of EVA. Now coming back to what was the purpose of this study, we choose the best result for each process, asphalt rubber and terminal blend. This was the optimum result, considering that we didn't want to have a very high viscosity. And we can see that we have better resilience, better frass, bigger softening points. And the amazing thing is that we even have higher penetration. And this is a terminal blend. Then we went to see the temperature susceptibility of asphalt rubber. This is a model that was developed by the Maryland University's model. We can convert the conventional measurements of penetration and softening points into viscosity results. We do like Alcomum graphs. And again, we can see the influence of increasing the percentage of rubber in the temperature susceptibility. So you can see here we have a natural binder, and we can see that this is very sensitive to the increasing of temperature. And here we have asphalt rubber with 20%, that is this line rubber here. Considering several types of modification, here we have our asphalt rubber, which is, the more horizontal the line is, the less sensitive to temperature variations the binder is. And we can see that an SPS heart has this kind of behavior, and here we have the F near to what were the results for a natural binder. Considering now asphalt rubber versus terminal blend, we have here our asphalt rubber and our two formulations for terminal blend that actually perform better than SBS and EVA, but are less performance than asphalt rubber. So the conclusions: asphalt rubber has superior temperature susceptibility, superior performance to temperature susceptibility. It presents excellent elastic properties measured here in this study by resilience. We know that success is extremely dependent on the type of formulation, wet or dry method, all the content of crumb rubber, reaction time, and techniques of production, and this is something that we have to be aware of when we use asphalt rubber. To what concerns terminal blends, from these results, we can say that it's not asphalt rubber and it hasn't the same performance. But the use of the polyphosphoric acid additives really improves the effect of modification of natural bitumen and SPS polymer. Also, polyphosphoric acid additives produce competitive terminal blend in comparison to SBS, but doesn't allow terminal blend to reach the performance in terms of temperature and best results of a standard asphalt rubber. Thank you.
Thank you, Ines. You can stay there for questions. Questions, please. Last session, everybody's tired, but a few questions. George.
Give you the microphone.
For me, this paper was a very timely and a wonderful paper, because this is a question that we are asked all over the world when we try to introduce asphalt rubber. It would be just nice that you continue this work and try to demonstrate in terms of fatigue life, the differences that can be encountered. So I congratulate you. This is clean, clear, in terms that are indisputable, that people understand in terms of all the tests that we already know, and we have a feeling for what they mean.
Okay, thank you.
Have you done anything in the mix itself, Ines?
No, only the binder.
Okay. This definition of terminal blend is not very clear-cut. People in Brazil they claim to use 15%. She said 10%, but